Hi everyone, it's time to start using our primary trig ratios, sine, cos, and tangent. Remembering that sine, of course, is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent, right? We remember SOHCAHTOA from last time. Okay, so I've added some approximate dimensions to these triangles, and what you might be asked to do is, you might be asked, what is the sine of A? Which means that we are being asked, what is the proportion, and so the angle at A, what is the proportion? Well, sine is opposite over hypotenuse, so what is the proportion of the opposite side to the hypotenuse side, right? So again, remember SOHCAHTOA. So that means sine of A must equal the opposite over the hypotenuse, and the opposite side is 12, the hypotenuse is 20. So we would just say, well, sine A equals, in lowest terms, 3 over 5, or perhaps as a decimal, 0.6, right? Now, that sine ratio, 3 over 5, or 0.6, is going to hold true for any right-angle triangle that has that exact same angle in it. And of course, any other right-angle triangle that did have that exact same angle in it would have to be a similar triangle, right? So of course, it would have the same ratio, right? If we looked at this one that has the same angle in it, right, 36 over 60, well, those are just scaled up, right? And this is, I just made up a scale factor of 3 in this triangle compared to this one, right? So whatever this ratio, 12 to 20 is, because it's a similar triangle, 36 to 60, it's all going to be 3/5. So we don't actually worry so much about this, what the side lengths are. We just say, well, anything with this angle, right here it's called A, but whatever has any right angle triangle that has this angle in it, there it is again, will always have this trig ratio for sine. The ratio of the opposite side to the hypotenuse will always be 3 over 5, or said another way, right, using the decimal or maybe as a percent, right? In any right angle triangle that has this angle, the opposite side will be 60% as big as the hypotenuse. No matter how gigantic the triangle is, no matter how small it is, this angle will determine that the opposite side will be 60% of the hypotenuse, or 3/5 as big as the hypotenuse, right? Or just saying that the ratio of the opposite to the hypotenuse will always be 3 to 5, right? There's a bunch of different ways of saying the exact same thing. Okay, so so calculating is not too bad. If I asked you, for example, what is cos of f, right? Here's angle f over here. What is cos of f? Well, cos is adjacent over hypotenuse, right? So the adjacent from f is the one next to it. There it is, it's 2. The hypotenuse in this case is 6. So in lowest terms, cos f equals 1 over 3, or of course approximately 0.33. Right? What if I wanted to do a tan ratio? Well, let's see. Tan of, tan of D. Tan, of course, being TOA, opposite over adjacent. Right? Here's D, the opposite of D is this side. The opposite, or the adjacent D is that side. So, easily enough, tan D equals 5 over 2. Or we could say that tan D equals, 2.5. Right? One way or another we can get the correct answer. Of course, most trig ratios actually don't work out quite so beautifully, right? If I had this triangle that I just drew, and this time I used a theta to mark the angle instead of a vertex letter. If I wanted to know, for example, what is tan of theta in this case, well, it's still opposite over adjacent, so it would be 21 over 17. And again, having a trig ratio as a lowest terms fraction is fantastic. If we wanted to know approximately what that ratio is as a decimal, of course, we would just punch it into our calculator, 21 divided by 17, and we would say, well, tan of theta in this triangle is approximately, so I squiggle that out, 1.24. Now, I wanted to show you a couple complete trig ratios, because a trig ratio always has 3 parts. It has the angle that you're referring to in it, and it has 2 side lengths in it. So I've drawn a triangle that I actually know exists. Sometimes I draw triangles that I just made up, but this one actually exists with these dimensions for sure, I know. So here is a triangle that has two internal angles of 60 and 30, and it has this side length of 5 and a hypotenuse length of 10. Okay, I know this is all true. So given this information, I could set up a sine ratio. For example, the sine of 30 degrees must be SOHCAHTOA, opposite over hypotenuse, 5 over 10. So sine of 30 degrees equals 1 over 2. Now, I think that's true. My calculator will actually confirm this for me. So if I bring my calculator over here, and I can't punch it in for you, but I can show what I'm going to hit. If on the, now this is an old school calculator, on this one I would have to actually punch in 30, 30, and then I would have to hit the sine button. A couple things here. Your calculator must show that it's set to degrees. It must say either DEG or just a D, right? Other things it might say are RAD or GRAD. It must say DEG. If yours doesn't, then you got to hit this button, I guess, until it does, the DRG button. So on my calculator, I would type in 30, and then I would hit the sine button. If you have a newer kind of calculator where you actually enter the stuff in first, you would actually hit sine 30, right? It might put the 30 in brackets. But regardless, once you hit the equal sign, it should tell you that sine 30 equals, and your calculator maybe can't speak in fractions, but it will tell you that it's 0.5, right? Similarly, a very similar thing, because I'm using actually the same sides, if I asked my calculator, what's the cos of 60? And I punched in on my calculator. On this old school one, again, I'd have to put in the 60 and then hit cos. On a newer type where you punch, or where you write in the entire line and then hit enter, you would do cos 60. You'll have to figure out which way your calculator works, but regardless, it should say that it's actually the same thing. It's 0.5. And if I look at my triangle, then I see, well, cos, again, SOHCAHTOA, adjacent to 60 over hypotenuse. So it's actually the same two numbers, equals 5 over 10. So it is true. My calculator and this triangle agree that the cos of 60 degrees is 1/2. So your calculator can tell you the sine or cos or tan ratio for any angle you want to throw at it, right? If you ask your calculator, okay, what's the tan of 50 degrees? Well, you just have to punch it in your calculator. Like I said, in mine, I punch 50 and I hit 10. There we go. And it tells me that the tan of 150 is approximately 1.19, right? The sine of, 11 degrees. Approximately 0.19, right? And the cos of, the cos of 45 degrees. 0.707 approximately. Often we write 2 or 3 decimal places for a cos ratio, or sine ratio, or tan ratio, as your calculator gives them. Let's say I had this triangle here, where all I know about it is that it is a right triangle. It has a 75-degree angle, a 15-degree angle in it. If I ask my calculator, what is the tan of 75? That will tell me the ratio, or the comparison, of the opposite side to the adjacent side. So punch that in your calculator, see what you get. And I get that it's approximately 3.73. Okay, and that agrees with my diagram. That's just saying that, right, if I made a fraction out of that, the easiest fraction I could make it would be 3.73 over 1. That means the ratio of this side to this side is going to be 3.73 to 1, or this side will always be 3.7 times as big as this side in any triangle of any size, as long as it's a right angle triangle and has a 75 degrees there. For example, I could also say, well, how about if I compare using cos of 75 degrees? Well, punch it in your calculator, and I find that it's approximately 0.259, right? So what's that, about 26%? That tells me cos is, of course, and 75 degrees. Cos is adjacent compared to hypotenuse, right? Adjacent over hypotenuse. And again, if it helps me easier to see, well, if I make a fraction out of it, this would be the adjacent side, this would be the hypotenuse side, or I could think of it this way, right? This is about 26%, 0.26-ish. So the adjacent side in any right angle triangle that has a 75 degrees, the adjacent side is always going to be about 26% as big as the hypotenuse, no matter how big or small the triangle is, as long as it has that 75 degrees in there. So that's just a couple connections that tell you, oh, these ratios are interesting numbers, but they actually, will relate to back to the proportions, the comparison between two of the three sides of the triangle. So what I might be asked to do using trig would be to determine unknown side lengths. Okay, so if I had this triangle, and I knew two things about it, actually I could probably solve for that angle pretty easily, but I do know for sure that this is 35 degrees, and I do know that this side is 7 centimeters long. If the question asked me, what is that side length x there? Well, I would have to first think of which of the three trig ratios is going to be helpful here. Well, it's going to be the one that compares these two sides, right? And if I'm talking about 35 degrees, then of course 7 is the adjacent side, and this x side is the opposite side. Well, which trig ratio compares opposite and adjacent? It's tan. So I'm going to set up my tan ratio, and I'm going to say that I'm finding the tan of 35, and I know that it equals something over something, opposite over adjacent, so it must be x over 7, right? And then I'll probably rearrange to solve for x. I'll multiply both sides by 7, of course. And so x equals 7 times tan of 35 degrees. And using my calculator, and again, it would be wonderful if I could actually do that on the screen, but I can show you what I would do. Well, I would find what probably tan of 35 is. So on this old school calculator, I'd hit 35 and then hit tan button, and that would show me what the tan ratio is. What actually is it? It should be showing 0.700, and then I would then multiply that, of course, by the 7, right? So times 7 and hit equals, and I get that x is about 4.90, right? 4.90 centimeters. How about if I wanted to solve for y and I still wanted to use this 35 degrees? Well, I would set up another trig ratio, but first I'd have to think, okay, I'm working with the adjacent side here, and here's the hypotenuse side. Which one of the three trig ratios uses adjacent and hypotenuse? So it's cos. So I would set up my cos ratio that includes the angle. It's 35 degrees. Includes the 7 that I know is the adjacent side, and I'm putting that over y. Now, of course, I can't solve for a variable that's stuck down in a denominator, so if you know about cross multiplying, then you know that you can just shove that up to the other side. How is that actually done? Well, that means that we're actually going to multiply both sides by y. They'll cancel out over here, and I will get that 7 on one side equals y times cos 35 degrees on the other side. Now I want y by itself, so I'm going to have to divide both sides by cos 35 degrees. And of course those will cancel out over here, and y will equal whatever 7 divided by cos of 35 is. So on my calculator I would hit 7 divided by 35 cos on my old school calculator, and then hit equals. 7 divided by 35 cos. It turns out that the cos of 35 is about 0.819. Hit equals, and I get that y equals 8.55-ish. So that's about 8.55 centimeters. Of course, again, if you have a newer calculator, you would probably be punching in, right, what 7 divided by cos 35 is, and then you could hit equals. So you'll just have to play around a little bit, see what kind of calculator you have, see exactly how it works. So I promise this will be an important skill both this year and next year, finding side lengths using trig ratios once you know an angle in a right angle triangle. And that's it for now. Next thing you will see in a new video will be how to work backwards and find an angle once you know some side lengths. So looking forward to that. See you later.